Hello and welcome to our next set of stats notes. We are on section 8.2. We're continuing with hypothesis testing. In the first section, we introduced the main ideas, how it all works, general approach for all the different types of things we'll do with hypothesis testing. In this section, we're going to focus and just drill down on population proportion hypothesis testing. So we're going to only be working with proportions, which means we're only working with z-scores. You'll see that, we saw that with confidence intervals, we'll see that with hypothesis tests, that when you're working with proportions, you tend to be working with z-scores. So we're going to be looking at, testing a population proportions. We're looking at your sample data, looking at the proportion of your sample, and then using that to try and test a claim about the proportion for the entire population. We are going to cover the p-value, critical value, and confidence interval methods. So all three. You could do a hypothesis with any one of the three methods. So most of the time it doesn't matter which method. The one thing is the confidence interval method can actually lead to different results. So the confidence interval method may lead to different results than the p-value or critical value. So if you do p-value or critical value, those two are pretty much interchangeable. But if you're doing confidence interval, you might end up with a different result. So whereas the confidence interval sometimes might tell you to fail, the p-value and critical value might tell you to not to fail, and vice versa. So that's what you have to be careful about. So usually you'll try and use which one is specified if you specify a method. Okay. Since we're working with population proportions, we're going to use this formula. So this is our formula for the test statistic. Remember, the test statistic is the value we use. If we're doing critical values, we look to check and see if that test statistic is more extreme, and then we reject. If we're doing p-value method, the test statistic is what we use to mark off the area, the percentage that we find. That's our p-value, our probability, and that value is what we use to check the significance level. So test statistics, we use either one of those ways. And then again, the confidence interval is when we really don't need the test statistic, because we'll use the confidence interval and then check the claim value, see if it fits in there. So just an overview real quick, the different methods. Just remember, so when you're doing a one probability test, first off, you always want to figure out what the null and the alternative hypotheses are. So you need to know those. Notice the significance level. Again, that will be provided. That's alpha. Pick which method you're going to go with. Are you going to do critical value, p-value, or confidence interval? Do your test and then state the result. Are you going to reject or fail to reject? If you're doing the critical value method, remember you need to find the test statistic z, because of z-scores for proportions. Find your critical values, and remember the critical values come from the significance level. So you always can base these off of the significance level. And we want to figure out if the test statistic is in the critical region. Remember, the critical region is the extreme region. So it's usually the tails, or I should not say always the tails, either one or two tails. So you always check to see if the test statistic in the critical regions is it extreme, because if it's extreme, that's when we reject. So that's what we do with critical values. If we're doing the p-value method, we still need that test statistic. So we'll calculate the test statistic z. We'll figure out the p-value from the test statistic. So we'll take that test statistic and figure out what the p-value is, the probability of getting that value, or something more extreme. And then we'll see if the p-value is smaller than the significance level. Remember, we said if the p is low, the null must go. If p is high, let the null fly. So we reject if the p-value is small enough. We're always checking to see, is it unlikely enough? Is it very unlikely? If the p-value is small, small probability, it's unlikely. If the p is small enough, that's when we reject. And the last method would be your confidence interval method. This is one method where you don't need the test statistic. So you just figure out what the confidence interval is, and you check if the claimed value, your null value basically, if that's in the interval or not. If it's not in the interval, that's when you reject. So check if the claimed value is not in the interval, because if it doesn't contain, that's when you reject. So null, not inside. If the null value, the claimed value is not inside, you reject. Okay, so all three of these methods work. Like I said, you might get a slightly different outcome with the confidence interval versus the other two methods. I'll try to cover all three of these in every problem, just to show all three of them a couple times. But when you're doing like the homework and the tests and stuff like that, you don't have to do all three methods. You can just do the indicated method. But you should be ready for all three methods because I can indicate which one. So you might need to find the test statistics. You can ask a question where you might have to use the test statistics. Maybe you need to use the confidence interval. So just depending on the problem, which one you have to do. So I'm going to do probably all three on these ones just for the practice. Now remember, before you do hypothesis test, we do have those requirements. So these are the requirements that must be met before you're really allowed to do a hypothesis test. The data has to be a simple random sample. So it's just the way you collect your data. If you had data that wasn't collected properly, you can't really do a hypothesis test. It has to have a binomial distribution conditions, where there's failure to success with only two options, the chances of each outcome are independent, stuff like that. And then both NP and NQ are greater than 5. That means that both the successes and the failures need to be at least 5. So if you don't have at least 5 successes and 5 failures, it really means your sample wasn't big enough, and you got to go back and try again with the bigger sample size. Okay, so let's try one. Let's do an example. So we have information down here. So use the given information to do to determine whether the z-test is appropriate, and then if it's appropriate, do your hypothesis test. So first off, they tell us it is simple random sample. The binomial distributions are met, so those things are good. We look for the number of successes and number of failures. Well, if there's 15 successes out of 40 sampled, right? So that's the number of successes, that's the number of sampled. That means there's 25 failures, right? Because 15 out of 40, there's 25 left over. So 50 successes, 25 failures, we're good to go. There's enough successes and failures. So conditions are met, and both success and failure greater than 5. So everything is good. So we're okay to do a test. So that's just checking that out first. Okay, so let's try and do the critical value method first. To do the critical value, we need to find the test statistic. Remember, our test statistic formula is this. We need to know p hat before we can find the test statistic. So first thing we're going to do is we're going to find p hat. So p hat, remember, is the probability of success, and you always find that by taking x divided by n. So we're going to take the number of successes divided by the number of samples. So I get 15 over 40. That's going to be my percentage of success for the sample. So 15 divided by 40, which is 0.375. So I get 0.375. I really should have a greater than on this one, because I was looking at this and we got 0.3. This is less than. Why did I not check that? Okay. Well, let's just do the numbers as is. Usually you wouldn't be doing a less than test when your sample is actually more than. So that's kind of a poorly written question. I made a mistake there. I was supposed to probably have a greater than here, but we'll test it like it's a less than test. We're pretty much guaranteed it's going to fail because our percentage we got from our sample is actually more than 0.3. So we kind of know already this one's going to fail, but we can go ahead and just do the test so you can see what it looks like. So after we get the test statistic, we need to do our test. So if we're going to do a critical value method, we need to figure out what the critical values are. So if I think about this being a less than test, if I have my distribution, doing a less than test, so I'm looking for this being my rejection region, I need to find my z-score right here that would mark off this critical value region and give me the rejection region. Now this is going to be based on our alpha. Remember, critical values are always based on alpha. So because we have 0.10, so 10%, this rejection region is going to be my alpha is going to be 0.10, so I need to find the z-score that has 0.10 to the left. Since these are z-scores, we're going to use inverse norm. Always use inverse norm for z-scores. And then the area we want to the left is 0.1, so we'll do 0.10, that's the area to the left. And there's an inverse norm. And then that's really all we need because the other values are the mean and the standard deviation. So we put the 0.1 area in there, 0 and 1 for mean and standard deviation, hit paste, and that gives us our value. So our z-score for this, our critical value, would be negative 1.28. So we're looking for the test statistic to be extreme enough that it would be beyond this critical value. So that would be our critical value, negative 1.28. So to find the test statistic, we use the formula, right? The formula for a test statistic. So we do Z is equal to P hat, which we said is 0.375, minus P, which is the 0.3, and that's the P given right there, over parentheses P, which is 0.3, or sorry, root 3.3. And then what's Q? Remember, Q is the probability of failure. So if we have a 0.3 chance of success, then the probability of failure would be 0.7. That'd be probability of failure. And then N, which is sample size, 40 would go at the bottom. So that's how we find the test statistic. So I type this in. I'm going to do 0.375 minus 0.3. I'm going to hit enter because I want the subtraction to happen before I divide. So now I'm going to hit divide. So you can square root 0.3 times 0.7 divided by 40. And we get, not surprisingly, 1.035, which is definitely not as extreme as negative 1.28, because if you take this value, the 1.035, it's way over here. It's it's above zero. It's positive. This is where our value is 1.035, and it's in the fail to reject region. It's not in the reject region. It's in the fail to reject region. It's even on the wrong side. It's just like way over here, because our percentage we got for our sample doesn't give us really any evidence at all. I'm trying to say it's less than 30%, and I get 37.5% for my sample. Well, then I really have no evidence to reject. So in this case, that value we got, this test statistic, is actually bigger, and we wanted it to be less than. So since our test statistic 1.035 is not the less than we're looking for, right? It's not less than that negative 1.28 critical value. We fail to reject. Okay, that's the critical value method. If we want to do p-value method, and a lot of times we will do p-value method just because p-value method is much better for being able to use technology. Here we had to kind of figure most of this out ourselves. We can type this in our calculator. We can do the inverse norm in our calculator, but the p-value method, you can really do most of it in your calculator. So if you want to do this critical value, the p-value method, with the p-value method, we can go to the stats option, go to the tests option, and scroll down until we find the one prop z test. So we want one prop z test. There it is. Oh, I want two. I want one. One prop z test. So it's proportion prop. Since we're working with the x's and the n's, we're not working with means. We're working with proportions or percentages. And z test, because with proportions we're always going to be doing z tests, and we're not doing an interval, right? We're doing a test. That'd be the big difference. There's a one prop z interval when you want to build the confidence interval, but we want to build a test. Okay, so what's the p0? That's the claim value, which is 0.3. X is 15. N is 40. And then we're doing a less than test. We probably should have done a lot more than test, but we're doing a less than test, which we'll see will definitely fail because we have such a big value in our sample. Okay, so that gives us the test statistic. So this same test statistic we got here, you can get from doing the one prop z test. So if I do one prop z test, it gives us the test statistic 1.035. It actually gives you the p-value, which is 0.849 or 0.8497. I guess you round to what you need, 497. And it gives us the sample proportion, 0.375, so this that we found up here. So you can see how a lot of this stuff, if you want to, you can actually get all that information from the calculator. The one thing the calculator isn't giving us that we had to do up here was the critical value. So it gave us, the calculator does give us the test statistic, does give us the sample proportion, it just doesn't give us the critical value. So really, this is the one thing that you need to be able to do without the one prop z test, is figure out what the critical value is, and all you need for that is the alpha, the significance level, because once you have the significance level and you know what kind of test it is, it's a left-tailed test, then you can find your critical value and just compare that with the z-score, the test statistic that we got from the calculator. So that's one of the nice things. So all this I could have done with the calculator. I did by hand once to show you, but from here on out I'll probably do the p-val method first, and then we'll just figure out the critical value and do that to finish off the critical value method. Okay, for doing the p-value method though, we get the p-value, and remember that the p-value test, we always compare the p-value with the significance level. So we're going to compare the p-val, which is going to be the 0.8497, with our significance level, which is the 0.10. And because p-value is bigger, that's when we say p is too high, then almost fly. I know it's a silly thing your book says, but it works. This is too big, so we let it go. We fail to reject the null. We can't reject the null because we don't have a good enough evidence. The probability of our value has to be so small that it's less than the 0.10 or less than 10%. If it's not smaller than 10%, then we don't have enough evidence. We need to have something so extreme. And again, we knew we weren't going to fail this time because our sample proportion was way too big. If we got a sample proportion like 0.2, way less than 0.3, then we might get a p-value where we could reject. But because our sample proportion was so big, and we're looking for something smaller than 0.3, we're in a bad shape. So we really don't, use this. Okay, or aren't going to reject, I should say. Okay, last one. Let's go ahead and do the confidence interval method. So if we go with the confidence interval, we can use the one prop z interval. The thing we got to be careful about is when you do the confidence interval, you need to make sure you use the right percentage. So if you get the right alpha significance level. So I go to my stats, my tests, and do the one prop z interval. Now, x is 15, n is 40. The confidence level in this case, we need to have the chart, the thing. So it's got 10% in this tail, right? 10%, which means it has to have 10% in this tail. So we actually are going to put 80% or 0.8 in the middle. Remember this thing about the confidence intervals, we talked about this in section 8.1, is that when you're doing a one-tail test, you need to make the tails on the confidence interval big enough that there's the same 10% in both tails to make it work. So instead of doing a 90% test, which feels like that would be natural, oh, it's a 10%, let's do a 90% test. No, you actually have to put 10% each tail to make this work so that you have 10% in this one tail. And then that means you're only with 80% here. So you're actually going to take away 2 alphas from 100%. So it's just taking away 1 alpha, you take away 2 alphas. So because this is one-tailed, we're going to do 1 minus 2 alpha to figure out the confidence level. So that's how we get this 80%. So it's not going to be 0.9, it's going to be 0.8. And that's how we'll calculate our confidence interval. So our confidence interval for this one is 0.2769 and 0.4731. And so again, we always look for, does the p-value, or not the p-value, sorry, I should say that, the claimed value, p, does that fit in our confidence interval? Well, 0.3 does fit. And again, if it fits in here, then we say, oh, we can't reject it because it fits. It makes sense. We built the confidence interval and the 0.3 fits inside there. So p equal to 0.3 fits inside, which in this case we fail to reject. And sometimes the confidence interval will do the same as the other two, right? In this case it does, but there are chances it might not. So that's why we always have to worry about them being a little different sometimes. But a lot of times they won't give you the same result. So we did 3 different ways. In all 3 ways we failed to reject, but we're not really surprised by that because, like I said, the value we got in the beginning was way too high. Probably should have had the less than turned into a greater than. But oh well, we just did it. It was like it was a lesson test, just for the practice. So again, one prop Z test will do your test. If all you need to do is test whether it passes or fails, this is probably the easiest method because you just throw in, the xn, whether it's a less than or greater than, that kind of stuff. You saw what I did, the stat test, one prop Z test. You should tell it what the claim value was, 0.3, this number of successes, number sampled, and whether you're doing a less than, greater than, or not equal to test. That's all you had to tell it. So it was pretty straightforward. And then you could calculate and get your p-value. And again, you just compare p-value with the significance level. And that's probably, I think, the easiest way, especially using your calculator. If you need to do critical values, because there are some test or homework questions that will ask for critical values. Again, you really just need the significance level to find the critical value. Think about what kind of tailed test it is. Here, this one was a left-tailed. We put 0.1 in this area, and then just did inverse norm to get our critical value. And if you need a confidence interval, you just run a one prop z interval, but you gotta be careful about what the confidence level should be. This one should be an 80%, because you need to have 10% on the left tail. Okay, let's try another one. But that's the idea. That's and you don't have to do all three on all your questions, so you'll just do one of those three on your questions. And that's what this homework's going to be all about, is just doing these hypothesis tests. Okay, give us more information, tell us to decide whether it's appropriate to do a z-test, and then, if it is, do one. Okay, so they give us, and they say, okay, number of successes 32, number of samples 35, looking at p-value 0.3, looking for greater than 0.95. And they say it is simple, random, and binomial distribution, which is what we always look for first, right? Binomial and simple, those are good. But then you notice, wait a second, there's 32 successes and 35 failures, and 30 out of 35. If I take that and I subtract 35 minus 32, that means there are 3 failures. And we know that you can't do this test unless both successes and failures are greater than 5. So this one, there's not enough failures. So we can't actually do this test. They didn't take a big enough sample. So in order to do this test, they're going to have to go back and they're going to have to collect a large enough sample. One that they have such a big sample, they end up with at least 5 failures. So if they went back and sampled 60 people, 70 people, they'd probably be okay. But 35 was just not enough. Not enough failures, can't do the hypothesis test. When your percentage you're looking for is greater than 95%, that's kind of a warning that you probably are going to use a larger sample size. The closer the sample size gets to like 0 or 100, or percentage gets to 0 or 100, the more your sample size is going to probably end up having to be to get enough successes or enough failures, because most of them in this case were successes. If you're at close to 0%, most of them be failures. When you're at 50%, you don't usually use big samples because it's half and half. So you only need like 10, and half is 5 and 5. So the closer this percentage is to 0 or 100, usually means you need a bigger sample size. So that's why they really were in trouble. Okay, let's try one that actually can work this time. Okay, so a manufacturer wants to ensure that no more than 5%, so no more than 5%, so it's a low one again. So hopefully they sampled a lot of their products are defective. They test 210 products. Okay, so they tested a lot, so that's a good sign. And they find 15 defective. So 15 is pretty small, but it's enough, right? So we have 15 successful, defective, successful in this case would be defective, which always feels weird, out of 210, which means there's hundreds of failed, which are not defective in this case. So we got plenty, 5 of each. We'll assume they did simple random samples and that they got binomial conditions met, which, it's either defective or not defective, so there's only 2 choices. So it makes sense. We're going to do 5% significance level, determine they have too many defective products. So we're looking to see if they have too many. So in this case, we're going to do a greater than test, because if they're looking for too many, we want to check and see if it's actually more than the 5%. If it is 5% or less, we're okay, but we're looking for more than. So we're looking for a more than test. So our null hypothesis would be that the percentage of defective products would equal 0.05 or 5%. The alternative in this case would be that the proportion is going to be greater than 5%. So we're looking at greater than test. Make life easier. Let's start off with the one prop z-test, because we saw that gives us most of the information we need to have. So do that first. Stats, tests, one prop z-test. In this case, p-value, the claimed value is 0.05. The number of successes, and this time would be 15. That would be the number of defective. It's the number of successes, and sampled would be 210. So 15 successfully defective products and 210 sampled. And here we're looking at a greater than, right? So we're looking at greater than 0.05. Okay, let's see what we got. Calculate, and they tell us that the test statistic for this one is going to be 1.425 if you round that. The p-value for this one is 0.0771. The proportion from our sample is going to be 0.07. So it is bigger than 5%, right? It's not that much bigger, but it's a little bit bigger than 5%. So looking at this, now we can do either the p-value method or the critical value method. When I do the critical value, so doing the critical value, we draw our chart and think, okay, we're looking more than, so we're looking at the right tail. Since they're doing a 5% significance level, we want this area to be 0.05 or 5%. That's going to be alpha in that area. And we're looking for the critical value to compare with their test statistic. Because this one, the test statistic, the prop test gives you the test statistic, we need the critical value. So to get this, we're going to do an inverse norm. Do inverse norm to find this when we're doing proportions. So z-scores. Area is 0.05. So we do 0.05 and 0 and 1 because these are standard normal scores. So I'll do my second distribution, inverse norm, 0.05, 0 and 1. And it's going to give me a negative, right? Because doing this like I have 0.05 on the left side. So I do need to swap that and turn it into a positive because I know I'm on the positive side because I'm doing the right tail. If I wanted a positive number, I could have done 95% because that's what's in this area. Remember the inverse norm only does area to the left. But I just do the area for the piece I'm looking for, and then just remember if it's positive or negative, because I think that's probably easiest. So this turns into positive 1.645. And that's because this is going to be a positive z-score. So we always just turn that into a positive after our z-score, because we did the flip-flop over the center, which is 0. So to get that symmetry and all that. Okay, that's our critical value. So we compare our critical value with our test statistic, and we say, is our test statistic extreme enough? Again, it has to be more extreme than our critical value. But our test statistic is 1.425, and our critical value is 1.645, and it's less, it's not more. So in this case, we fail. In that case, yeah, it doesn't. So far it's saying, no, it doesn't. So we should probably expect the same thing with our p-value test. So using the p-value method, let's look at that. P-value method, again, this is our p-value from the 1 prop z test. And we always compare the p-value with the significance level. That's our alpha. So we're going to take that, we're going to compare, we're going to say, the p-value, is it less than alpha? Well, it says p-value is 0.0771, and alpha is 0.05. Remember to turn this into a decimal. You don't want to compare percents and decimals. You want to go the same kind of number. And you see that that's actually bigger, right? 0.0771 is bigger than 0.05. So it's too big, and so we fail again. Because remember, you only reject with the p-value method if your p-value is small enough. And it wasn't smaller than 0.05, so it wasn't small enough. So if we fail to reject. And then confidence interval, if you want to do the confidence interval method, again, we have a one-tailed test. So when we think about building our confidence interval, we think about how we want 5% in this test, 0.05, which means that the other tail has to also be 0.05. And so in the middle here, we actually have 0.90, right? Because we had 5%, 5%, so that's 10%. There's only 90% left. So even though we took away 5% for one tail, we have to take 5% for the matching other tail to get the proper confidence interval. So we're going to use this to get our confidence interval. So we're going to do the one prop z interval with that 90% and see what we get. So stats, tests, one prop z interval. We're looking at x is 15, n is 210, confidence level is 0.9, and we calculate. We get confidence interval goes from 0.0422 to 0.1007. Does that contain our percentage? Well, our percentage is 0.05, which is inside there. So that's the claimed value is 0.05. It's inside their confidence interval, so we fail to reject it. It makes sense. 0.05 falls within the interval we built, so we let it fly. We can't disagree with it because it's a possibility. So contains p equals 0.05. The significance level, or sorry, the p here, no more than 5%. Not that one, this one. And so we fail to reject. So all three of these, again, fail to reject. And again, you don't have to do all three when you do the test. You just pick one. But if they're asking you for the critical value, you'd have to find the critical value. Ask for the confidence interval, you have to find the confidence interval. If they just ask you to test it, yeah, you could just do a p-value test and call it good. So it really depends on what they're asking for. And again, I'm just doing all three just to show you. I think I only have one more page, so that's why I'm kind of taking my time on each one of these, because this is really all this section is just doing hypothesis tests. That's the big idea. This last one, the big difference here is that sometimes they'll give you the sample size and they'll give you the proportion, but they don't give you the number of successes. So instead of giving you x and n like we've been doing, sometimes they'll just give you p hat and n. Well, that's not a big deal, because if you know the proportion and you know the sample size, you can find the number of successes x and multiplying the number of sampled times the proportion. So this is what we do if you're looking for the number of successes because they didn't give it to you. So if you get a problem like this one, especially because on the calculator you saw you had to put in x and n. So if they don't give you x, you're kind of out of luck with the calculator, except for they give you enough information to find it. They tell you the sample of 240, 50% of them were successful. So we know that this is n and this is p hat. So to find x, we're just going to take n times p hat. So we're going to do 240 times 0.15. Make sure you turn your percent into a decimal before you multiply. And that will give us our number of successes. So I'm going to do 240 times 0.15, and we see there's actually 36 successes. So 36. So that's the number of successes. In this case, since there's 36 successes out of 240, you can still see there's hundreds that are failing, so that's fine, because we have enough successes, enough failures. Again, we'll assume that they have a nice binomial distribution and simple random sample. Unless they say that otherwise, we're going to assume that's true. Okay, so we can do our hypothesis test. So we're going to do our one prop z-test. Put in this information. So stats, tests, one prop z-test. So again, now we have the null. They're claiming, I guess I didn't even get to that point. It says, high school teacher claims that about 20% of students take a year off and then attend college. Tester claim with a significance level of 1%. So I guess the null in this case, I should mention real quick, the null would be that the percentage is equal to 20%, so 0.120. The alternative in this case, it doesn't say whether he's looking for them to be less or more than, right? He just says a high school teacher claims 20%. So I think in the alternative in this case, we'd actually say P is not equal to. We do a two-tailed test for this one, because we don't have any reason why they're looking for less than or more than. So there we'll say that null is equal to 0.2, the alternative is not 0.2. So our null would be 0.2. Number of successes we found is 36. Sample size is 240. And we're going to do a not equal to test. So not equal to. Okay, so from that information we get the test statistic, negative 1.936. We get the p-value is 0.0528. We get p hat, which is 0.15, which we already knew, so that's not really new information. And n is 240. So all that last two are kind of restating things we already knew. It's kind of nice to make sure you typed it in correctly, because if they don't match up, then you know you didn't type something correctly. Okay, so they gave us the information. Again, if I was going to do a critical value method, I'd think about what my chart looks like. Since I'm doing a two-tailed test, I'm going to have two tails, and this 1% is going to actually get split between the two tails. So I'm going to have 0.005 and 0.005, because with 1% split between two tails, each of these are going to be 0.5%. So if you move the decimal, that's 0.5%, 0.5%. So because we're doing a 1% test, we only end up with 0.5% of each tail. So I need to find out what these z-scores are. And this would be the positive one, that would be the negative one. They should match. So I'm going to do an inverse norm of 0.005, because that's how much I have to the left for this one. 0, 1 for the mean and standard deviation. And that'll tell us the critical values. So the second distribution, inverse norm, 0.005, 0 and 1. And there we go, we get negative 2.576. So that's what this score would be, and then the positive would be just positive 2.576. That would be negative z, this would be positive z. Okay, so those are critical values. And again, to test this, we take the test statistic and say, is it more extreme? So is the test statistic more extreme? Well, in this case, negative 1.9 would actually land in the middle. So this value right here, negative 1.9, would be on the negative side, but it's not going to be as negative as negative 2.56. So negative 1.9 would be like here. And so this would tell us that we failed to reject it. Did I pick all ones that fail? I don't know why I picked everything that fails. I need to go back and redo these notes just to make one of them pass, where you actually get to reject, but all these ones are failing. So, if it had gone beyond the z, that's what we ended up rejecting. Okay, so that was the critical value approach. If I want to do the p-value approach, I'll use this number for my p-value. So remember, p-value compare with the significance level. So I would just compare p-value and alpha, the significance level, alpha, and see what happens. Well, here I have 0.0528, and here I have 0.01. And the p-value, again, is too big. Again, we fail. Yeah, I picked a bunch that fail, so this one fails to reject. And then lastly, if I was doing a confidence interval, so confidence interval method, I do my one prop z interval. And think about the fact that this is the shape, and I have in these two tails, together they need 1%, so 1% together, so that each tail is going to have that 0.005. So this one, my middle piece, is actually going to be 0.99. So this one, you'll notice, we just subtracted this alpha once to get 99%, because we are doing a two-tailed test, and that's the difference. When you do two-tailed tests like this, you don't subtract the 1% of the alpha twice, you only subtract it once. So this is just the 1 minus alpha because it's two-tailed. That's how we're getting the middle here. So saying, hey, if alpha is 1%, subtract one of those, because you're going to split it between the two anyways. You're going to split it between the two anyways, and that will give you the confidence level. So we're going to do a one prop z interval with 99% for our significance level, or confidence level. So we're going to do stats, cut tests, one prop z interval. Our number of successes was 36. We figured that out. 240 was the number sampled. And then, 0.99 is a confidence level. If we calculate, we get 0.0906 to 0.2094. And then, as always, we look at P, the claimed value P, the claimed value, and say, does it fit inside? Does 0.20 fit inside there? Well, yes, it is, because this one goes all the way to 0.2094. It's a little bit higher. So it contains that claimed value of 0.2. So we failed to reject. Okay, and that's it. So 8.2 is all about doing hypothesis tests. Again, we have 3 different methods. And I showed you all 3 every time, but like I said, on the homework, you don't have to do all 3. Unless you want to practice, you can do all 3 just to practice. The big thing is, the reason I can't just say, just do p-value and call it good, is because they might ask you what the confidence interval is that you would use. They might ask you what the critical value is. So it's really easy, if you're writing a homework or quiz or a test, to make you do these other methods by asking for the confidence interval or asking for the critical value. So you need to be ready to do that. Again, most of the time, I think nowadays, most people just use the p-value approach. It's a little bit easier. You can see how you do the calculator. All you have to do is check that value with the significance level, and you're done. So most people, I think that's what they use, unless there's a reason they have to use one of the other 2. I'm just going to warn you, because on the homework quizzes, the test, sometimes they'll ask for the critical value, sometimes they'll ask for the confidence interval. So you should practice those when you're doing the homework. Yeah, you can definitely do the one prop z test and get an answer pretty fast, and that's great, because then you'll know whether to reject or fail to reject. But you should also know how to find the critical values, and you should also know how to build that confidence interval. So that's why I wanted to go through all 3 each time. Okay, so that's it for 8.2. This was all proportions, notice. So everything we dealt with here was those x's and n's. We're looking at p's and p hats. 8.3, we're just going to shift, and we're going to talk about how to do means. Because the means, we're going to deal with the sigma unknown situation again, like we did with the confidence intervals. We're going to be working with t-scores again with the means. And that's something you'll see, hopefully you noticed and you picked up on and you'll remember for the exam, is that when we're doing confidence intervals or hypothesis tests with proportions or percentages, the p's, it's always z-scores. And we do it with means, it's always t-scores. So I'll mention that again on the next set, but that's something I really want you to pay attention to, is when you use z-scores versus when you use t-scores. Okay, that's it for this section. I'll see you on the next one.